In this video, we're going to work out the next few problems from our exponential growth and decay applications. The fourth one on our sheet is this problem. $22,000 is invested in a savings account, but this time it's earning 2.5% interest, and that's compounded continuously. Whenever you see that compounding continuously, you need to remember that we're going to be using the formula involving E. All right, continuously compounded interest, think E. So we got to use the balance is equal to the principal times E raised to the RT. In this case, you don't see N showing up at all. You're not compounding a fixed number of times per year. In this case, your interest is earning interest all the time. It's earning it continuously. Now put in our information. We know the principal is 22,000. The interest rate is 2.5. Convert that to a decimal, and we see this is our formula. The balance after 20 years, that's not too bad. We want to plug in t equals 20. And then we're going to solve for the balance and determine what the balance is. So we're going to plug in, take a calculator out, and compute that number. In this case, we're getting it to the nearest cent to be 36,271.87. And that's it. That's all we got to do for the first part of the problem. Write the formula down, plug in for the appropriate value, in this case for t equals 20, and then determine the balance. The second part of the question and the third part are a little bit more difficult. We have to use logarithms to answer these. In this case, we want to know how long will it take for the balance to reach 30,000. Our formula is still the same, but now we're going to be plugging in b equals 30,000 and then solving for t. Okay, there we plug in 30,000, we get it equal to 22,000 times e to the 0.025 t power. We want to isolate the expression with the t on it. That's just the expression involving e. The 22,000 is not affected by that exponent. So we divide both sides by 22,000, then simplify, and we get that we have e to the 0.025 t is equal to 30 over 22. Now here again, we want to convert from exponential to logarithmic form. Remember, the special notation ln stands for the natural logarithm. That's log base e. So the conversion from logarithmic to exponential, or vice versa, is given by this equivalence. So we're going to say now our exponent v is 0.025 t. Okay, the base is e, or ln, and then what's going to go inside the logarithm is the 30 over 22. And then we're going to solve this linear equation for t by dividing by 0.025. And that gives us our value for t. It's the natural log of 30 over 22. And that's all divided by 0.025. And that is about 12.4 years. Okay, rounded to 4 decimal places, that's what we have. Okay, so we do the same thing in the next example. We're going to be, next part of the problem, we're going to be wanting to know how long will it take. So that's asking for a t value. We want to have to solve for t in our formula. This time we're going to put in 44,000 because we want to know how long it's going to take to double. And double our initial investment is 44,000. So now we're going to isolate this for t. Again, we're going to divide by the 22,000 first. But now notice we get 44,000 over 22,000. That comes down simply to 2. So we get e to the 0.025 t equals 2. And then we want to convert this from exponential to logarithmic form. And we get the equation 0.025 t equals the natural log of 2. Now dividing by t, or by 0.025, we get that t is the natural log of 0.2 over 0.025, and that's approximately 22.7259 years. Makes sense, it's more than we got in part B, because we're going to double it in this case. Next example, we want to say the function is modeling some growth where t is time in years. In this case, we want to know by what percent does the population increase from one year to the next. And this could be one around it to 4 places. Here we're going to take use of the fact that any exponential model can be put in the form 1 plus, or the initial amount, times 1 plus r to the tth power, even when it's base e. So what we want to do is look at our base and recognize we can rewrite this e to the 0.067 t. We can think about that t being pulled off a little bit, and then take a calculator out and evaluate that. e to the 0.067 is about 1.069295478. And now what we want to do is set these two equal. We want to set our base equal to 1 plus r. So we're going to say 1 plus r equal to our base. Solve for r by subtracting 1 from both sides, and then convert that to a percentage. So move the decimal place over, and we see that we're increasing by about 6.9295478% from one year to the next. Okay, we kept a few extra decimal places, and that's fine. The next question is similar. It wants to know if you've got this exponential, in this case it's decay model, by what percent does the population decrease from one year to the next. That exponent on e there, the negative 0.18, is the continuous growth, or in this case the continuous decay rate. We want to convert it over and know what this percent decay rate is. Right? So we're going to take our formula, and again we want to evaluate our base, write down our base. Instead of writing e to the negative 0.18, we're going to put in the decimal approximate for it. That's what the calculator will tell us. And then we get our base, and we want to set it equal to 1 plus r. Subtracting 1 from both sides, we can see we're going to get a negative result. And that makes sense because we're talking about exponential decay here. So we're going down in this case because of the negative growth rate by 16.475978% from one year to the next. That's how much the population is going to decrease from one year to the next. The seventh example on there gives us a model. In this case, it's the amount of plutonium stored in a vault T years after storage. So T is time in years, A is the amount of plutonium in pounds. Now we're being told that there's 820 pounds initially. That is A sub 0. Alright, that's the initial amount. If you plug in T equals 0, you're left with A sub 0 there, because e to the 0th power is 1. So we're going to get 820 for that. So our model is really that the amount A, or A of T if you want to write it that way, is 820 times e to the negative 0.0073 T. Now what we're going to do is, to answer the question, how long will it take for there to be 200 pounds in there? You're going to plug in the amount A for 200 pounds and then solve for T. That reduces to this equation. We want to isolate T by dividing by 820. The 820s cancel out, and we're left with 200 over 820, which simplifies to 10 over 41. So we get e to the negative 0.0073 T equals 10 over 41. Again, we want to convert from our exponential to logarithmic form. The base here is e, so we're going to be converting to log base e, which is natural log. In this case, the exponent's negative 0.0073 T, so we get that is equal to the natural log of 10 over 41. Now divide to solve for T, and then we can use a calculator to approximate the value, and it's about 193.28589 years. And that's the end of that example. That's all we were asked to determine.